Welcome, ladies and gentlemen. May I have your attention, please? Thank you. At this time, I'd ask that you raise your hand if you did not get red marks for today, the 21st. Okay, let's go ahead and begin our discussion. The same concepts that we've been using to find the exact area of an irregular shaped region using definite intervals is now going to be extended, right, in order to find the volume of irregular space shapes. And so that's where we're headed today. Let's go ahead and take a look at our Bellwork today. Here we have an interesting region. It looks like it's bounded by two different parabolas, but they're both oriented sideways. They're both y squared quadratic parabolas as opposed to our traditional x squared that we're used to thinking of. Let's go ahead and set up a definite integral and find the exact area of this irregular shaped region. So we have this irregular shaped region here, and we're going to find its area exactly using the definite integral. All right, so I went ahead and made a little bit more space. So I'm going to go ahead and again practice with my UW-Baraboo County shading class. I've been practicing for the weekend, and you can see, I hope, a stark improvement. So if I had my region here, my pepper green region, and I'm going to go ahead and find its exact area, does it make sense, right, to use my base shape of rectangle and scan this region from left to right, or does it make more sense to scan this region from bottom to top based on the shape of this region? Well, did you integrate with respect to x or with respect to y? Did you with respect to x or with respect to y? Sophia?
Y.
With respect to y, how come?
Because it's like sideways and you can mix it.
Yeah, absolutely. If we drew a horizontally oriented rectangle that is turned on its side like that, right, we could make sure that no matter where we drew, oh wow, you see that? That's pretty cool. Oh, that is so is that. No matter where we drew this horizontally oriented rectangle, it's always bounded on the right-hand side by the same boundary curve. I'll do that parabola in red. And no matter where I draw it, it's always bounded on the left-hand side by this green parabola. Therefore, Ella's method, right, of scanning from bottom to top throughout the region, from lowest y value to greatest y value, and integrating a rectangle's height that's horizontal times its delta y width that's a small vertical step to create the area of a single rectangle, and then summing all those individual rectangles areas up to get the irregular shaped green region is the way to go. So let's go ahead and rearrange these to solve them for x, so that I have functions with y's in them. So we can, in general, now integrate our right curve minus left curve. And so our form is to integrate from the least most y value, call it c, up until the greatest most y value, call it d. And we'll go ahead and do my right curve solve for x. I'll go ahead and, so that I have y's in it, I'll go ahead and call that r of y, minus my left curve, solve for x, so I'll call that L of y, so that I have y's in it. And then integrate that with respect to y, that is bottom to top. And so that's the general form we're looking for. It looks like x, right? X. Oh. So this is my red curve equals 2 minus y squared. This is my green curve. My green curve, x equals negative y squared. All right. In order to set up my, yes, Jake?
Should your coefficient on y squared in the top one be 3?
Absolutely. I've got this, I've been bad with numbers.
That's fine.
Ever since the beginning, so this should be 3. Perhaps I was talking while I was writing, always a hazard for me, right? Always a hazard. So minus 3y squared. Thank you, Jake, I appreciate that. That's my fault. All right, so let's go ahead and consider what my limits c and d will be. In order to do that, I need to set up and solve a system so I can determine those points of intersection, right? I need to know what points where they intersect so that I can decide what my lowest y value is of the region. So how do I do that? Easy. We'll set the red curve equal to the green curve and find that blue point of intersection. So here we go. I want to know when 2 minus 3y squared is equal to negative y squared. Isn't that just in the festive spirit? So we'll go ahead and add over that 3y squared, and I'm getting 2 equals 2y squared. and I'm getting y squared equals 1, and I'm getting y equals the positive and negative square root of 1, which is 1. Which means that this y coordinate of this point must be negative 1, and this y coordinate of this point must be positive 1. Where, pray tell me, would I go to find what the corresponding x coordinate is in each of those points of intersection? Well, to my curves that we just solved for x. So it looks like 2 minus 3 times negative 1 squared is 2 minus, carry the 9 square root of the inverse tangent, negative 1. You guys getting that? Negative 1? Awesome. So negative 1, and also negative 1. I'm sorry, positive. Great. So what are we going to do? Let's go ahead and set up our definite integral. We're going to integrate from the least most y value, negative 1, to the greatest most y value, 1. Our right curve is given by the red curve. Solve for x. That's x equals 2 minus 3y squared. Minus my left curve, solve for x. That's given by the green curve. That's going to be my x equals negative y squared. And I want you to go ahead and take a look at your paper. Raise your hand if you had this definite integral set up. So you had right curve minus left curve, and you had y's in it. That's great. So our right curve minus left curve, and now we're ready to go ahead and integrate. And we can do this exactly and algebraically by hand in accordance with the fundamental theorem of calculus. I would probably rewrite my integrand function to produce an easier integral. So I'm going to go ahead and do from negative 1 to 1. And I'm going to go ahead and combine like terms inside my integrand function. 2 minus 3y squared minus the negative y squared is the same as 2 minus 3y squared plus the positive y squared. So I'm getting 2 minus 2y squared. My simplified integrand, is that what you guys are getting? Awesome. Did anybody utilize the symmetry of the region to integrate from 0 to 1? So Sammy did, nice job. So we could always integrate from, because of the symmetry of my region, that is the top half above the x-axis, is congruent, right? Congruent, that is same size and shape as the bottom half beneath the x-axis. We could integrate from 0 to 1 and double it, but since most of you did not do that, we'll go ahead and carry on like this. Sammy, I'm on with you. That looks like an easier way because that lower limit plugging into 0 is a lot easier for my eval. All right, let's go ahead and do it. Find an antiderivative function. An antiderivative function for my integrand function and share with the class when I call on you. So everybody get ready. Even if you didn't get this far, I need an antiderivative function for that integrand. So what would that look like? Riley?
2y minus 2/3 y.
Awesome. Raise your hand if you had the same thing for that antiderivative, and you were going to say it. I just didn't call on you, but I will next time, so don't worry. And now we don't have to include a plus c. Thank you, Riley, so long as we include, right, our limits of evaluation here, negative 1 to 1. Top limit all the way through. So here we go. We'll put the 1 all the way through. I get 2 minus 2/3 minus lower limit all the way through. Lower limit all the way through. I get 2 times negative 1 is negative 2. And then negative 1 times negative, I get plus 2/3. So it looks like I'm getting 2 plus 2 is 4, minus 2/3, minus 2/3, minus 4/3. Go gadget arm. So it looks like we're getting 12/3 minus 4/3 is 8/3. I'm getting 8/3. Is that right? 2 and 2/3, 8/3. Awesome. And we want PDF mode. So I just distribute my negative 2 and combine my terms there. So minus negative 2 is plus positive 2 plus the 2 in front is 4, and then I did my fractions. Negative 2/3, negative 2/3 minus 4/3, and then common number. Awesome. What questions do you guys have about our Bellwork today? Nikki?
How did you get from the second red down to the one with the bluey green?
We took this upper limit, positive 1, and substituted it in my antiderivative function everywhere I saw y and evaluated, and then substituted my lower limit, it was where the green came from, into the same antiderivative function, and then subtracted the 2. So this middle comes from the fundamental theorem of calculus. This green only comes from the lower limit eval. This blue in front comes from the upper limit eval. Good. Other questions? All right, the same notion of taking a definite integral and finding the exact area of this irregular shaped region is now going to apply as we find the volume of the irregular shaped solid. But first we have some housekeeping to attend to. And so you guys should have already turned this in with the substitute last time, the area between curves practice, and the easier indefinite integrals worksheet stapled together. And I found those on my desk. I just haven't recorded them yet, but I did find a pile of those on my desk. What we're going to do is go ahead and turn in OTL 9C. And so again, we'll go ahead and start the stapler. If you guys can kindly staple those together. We've got the AP Calculus derivatives 1 through 25. I did change the bottom question to a log base 10, and then the last question, number 25, to a secant squared, because we didn't have logarithmic differentiation yet.
Wait.
Yeah, I changed it to the one on the answer. Sorry.
Oh, okay. Okay.
And what number was that?
42.
But I know a CPR doctor will make it a lot. It's a lot.
Okay, ladies and gentlemen, as you're waiting for the stapler, if you could kindly direct your attention to the smartboard number 14. I changed from a hybrid function that includes both a variable x in the base and in the exponent. So I changed that. And also, which we're not there yet, we'll get to that in logarithmic differentiation in unit 9. And number 25, I changed away from the logarithmic differentiation complex product quotient into a secant squared. And so everybody, if we wanted to check these answers, they were not provided on the key because I changed them after the fact. We know that my f prime of x can be gained by differentiating this logarithmic function. The problem is that my logarithmic derivative rules only include the natural log of the function. And right now, this is not a natural log, but a common log base 10. And so the easiest way before differentiating f prime would be to rewrite this as a logarithmic function using my change of base formula. That is to say, the log of any base b of an input a is given by the natural log of the input a divided by the natural log of the base b. In this case, the base is 10. So a quick rewrite just for my logarithmic properties and change of base would be to rewrite the same exact function in blue in red using natural logs. This would be the natural log of cosine of x over the natural log of 10. And so this is just the change of base formula that allows me to rewrite that with a different base. I choose ln because we have an ln rule, right? A natural log because we have a natural log rule. Now, let's say you don't remember the change of base. You could have rewritten this as 10 to the y equals cosine of x, right? And then differentiate using implicit differentiation to solve for y prime. In fact, we're going to do that in one of our Unit 6 activities to generate subsequent rules. In any case, now we can differentiate. I know that this 1 over ln 10 is simply a constant multiplier, so I'll pull that out in front so I don't trip on it. And then now apply my derivative words to the derivative of the natural log of cosine of x. I know the derivative of the natural log of a function is 1 over the function times the derivative of the function. So I'll do 1 over cosine of x and then times negative sine of x, and then we can do a regroup. So my final answer, f prime of x, would be given by negative tangent of x, or negative 1 over ln 10, maybe would look better, tangent of x, and that looks PDF. Does that make sense for number 14 now? So we would just use change of base to rewrite my original log. Great. Let's do number 25. Number 25 is, gosh, great candidate for the chain rule, eh? So let's go ahead and rewrite 25 where we have a little bit more room. So number 25 is x with secant squared of 4x squared. 3x to the fourth, so close. Let's do it. I know the derivative of composition of functions, the derivative of the overall function with the inner function, then times the derivative of the inner function. This overall function is not a trig function. What? But I worked so hard to memorize my trig rules. I know that tangent goes to secant squared, right? Right? And I know that secant goes to secant tangent. But overall, this is a power rule, where my base is secant of 3x to the fourth, and my exponent is 2. And so yet again, it would be useful to rewrite this original blue, as a function that it's easy to see, right, my base and my power. So I'm going to go ahead and rewrite this as a power function. This is overall a squaring function, where I'll use my power words. My inside function is secant of 3x to the fourth, and my innermost function is 3x to the fourth. So here we got a chain rule, right, with 3 links. So let's go ahead and do it. The derivative of a power function is the exponent times the base raised to 1 less times the derivative of the base. The base of this power function is secant of 3x to the fourth. The derivative of the base, secant of 3x to the fourth, in blue is a trig function. Now we get to use our derivative of a trig function. The derivative of secant is secant tangent. And so this is times secant of angle times tangent of angle. It's just that my angle wasn't x, right, or theta. My angle was 3x to the fourth. Itself a function of x. And so my final piece of the chain is to multiply by the derivative of my angle. And the derivative of my angle is 12x to the third. Oh gosh. Can we fit it? It's going to be tight. Yeah. Awesome. So my final answer then, f prime of x is given by, yikes, 12 times 2 is 24x cubed. And then you guys are going to go crazy and do this, right? Secant squared of 3x to the fourth, tangent of 3x to the fourth. Any order, right? We'll typically put that power function first. Did you guys get that? Yay! Good job, you guys. Awesome. Okay, by now you should have an ample opportunity to staple your ample opportunity to staple your derivatives worksheet with your integration practice packet. Make sure your name is on there. Let's go ahead and pass from the back to the front, please. Infinite campus score box, nice and big, around the nearest half point. Can we go to stapler?
I actually have 2 things to say.
Thank you, Brandon.
That's number 9C, yeah.
This is OTL number 9C. Where?
In green.
Down in green.
Email.
Yeah, I did. You today, I just put OTL.
Thank you. All right, pass them those por favor.
Got one more. Wait a second, Mr. Fritz. Yeah.
Mention you to play the blank game.
So ready.
Thank you, ladies and gentlemen. I appreciate your help. Okay, let's go ahead and get going for today. So what I want you to do is think back to how we use calculus to determine the area of an irregular shaped region. And so when we first started our definition, all right, our definition for the definite integral relied on a simple basic shape for which we knew a formula for. And that was the formula for the area of a rectangle. Everybody knows the formula for the area of a rectangle is base times height. What we did is we did the height of a rectangle times the width of the rectangle equal its individual area. And so somewhere in my region we could get the typical height of a rectangle by considering f of, I called it c sub k. Or the height of a typical rectangle, and we multiply that by delta x sub k for the width of that same typical rectangle. Together, this product represented the area of a single rectangle. Then what do? Well, we went ahead and summed up, right? We summed up all of the areas of those individual thin rectangles, right? From the first one up until the nth one to generate an approximation for, right? An approximation for the area of the region. And if we let the number of those rectangles go to infinity, that is, evaluated the limit as n goes to infinity, right? That would be the same as delta x shrinking towards 0, the width of those rectangles shrinking towards 0. Then I'd fill up that space exactly, right? I'd have no more jagged overcounting edges or sawtooth undercounting edges on my edge of my region. If I let the number of rectangles go to infinity and their width shrink to 0, I'd fill up exactly, right, the area of that region inside, and I get its area. And so this is our general definition for the definite integral, which in turn is equal to the integral from a to b, the leftmost x value, right, of my region to the rightmost x value of, and now here it comes, this f of c sub k, that is the height of a single rectangle in there, now is given in generalized form as the value of the function, right? The height of the function is going to give me the height of the rectangle, multiplied by delta x sub k, gave me the area of 1. Well, now, as delta x shrinks towards 0, now we're left with that infinitesimal, that dx. That dx comes from the limit as delta x shrinks to 0 of that delta x sub k, generalized into dx, the differential, and now we have the definition of the definite integral, and that gives us our exact area of any irregularly shaped region. But what about volume, right? What about volume? So in volume, we're going to apply the same notion. But first, I want you to think back to some space shapes that we already have formulas for. So let's go ahead and consider this. It's not showing up very well in the light, but I think we all recognize this, right? From our 12-ounce curls on the weekend that you guys do. Oh, root beer, right? Of root beer or Mountain Dew. Ask Scott Browse, and he's like, about the root beer. No, about the Mountain Dew. He's like, gods. I think if he could, he would definitely two-fist, right, the Mountain Dew, right, one in each hand. Okay, so we're going to think back to our volume formula and go ahead and share with the class. What's the volume formula be for this shape? You can tell your partner, because right now I know you're getting anxious because I'm going to call you. All right, so what do you guys have for the volume formula for this space shape? Michaela and Sophia?
Pi r squared times
Pi r squared times the height. Wonderful. So pi r squared then would be the area of the base in this cylinder, and then my height, right? My height h, right, would be the height of that cylinder. Awesome. Raise your hand if you had the same thing. So we had the same thing. Perfect. Let's go ahead and consider if we had a square prism. Could we generate a formula for its volume? Well, certainly. The volume V of this square prism, go ahead and tell your partner. How can we generate a formula for that? What would you have for that, Jake? X squared times height, where x squared then would represent the area of this base. Oh boy, we're going to go like that. And then multiplied by the height. Again, we could do that in red. Great. So then, what about this pentagonal prism? Well, without having any dimensions here or variable labeled, in general, all of these are using the same general form. If we could generate a formula for the area of the base here, right? Call it big B, and then multiply it by the height of the solid, call it H. That big B base area multiplied by the height H equals the volume of the solid. We're going to apply that same notion now to irregular shaped regions. And so if we let this be, It's coming, but you don't know it. But if we let this be B, if we let that be B, then my volume will be given by that base area B multiplied by my height. This is exactly what we're going to do to find the volume. So instead of just taking, right, the height of a rectangle and then multiplying it by the width of that rectangle, we're going to take the base area of a single slice, like the slice of a loaf of bread, and multiply it by the width, the thickness of my slice, if you will, to get the volume of a single slice. And then if I sum up the volume of this slice, plus this slice, plus this slice, plus this slice, eventually I'd have the whole loaf, if you know what I mean. And so that's what we're going to do as we apply our notion of definite integrals to volume. So here we go. Area, we saw that we took a typical height of a rectangle, f of c sub k, multiplied by the width of that same rectangle, gave us the area of one rectangle. Then we summed up all of such areas from 1 to 10 and considered the limit as the number of rectangles went to infinity. That resulted in a definite integral from a to b of f of x, the generalized height of a rectangle, multiplied by f of x, the width of any infinitely thin rectangle. Volume is going to be applied the same way. It's just that my height of a rectangle here, right, f of c sub k or f of x, is now going to be not an f of x function value, but an a of x, an area of a typical slice, a cross section. If we took an orange, right, and we sliced it somewhere in the middle and turned it toward face you, it's have a circular cross section. Right? It would have a circular cross section. If we took a loaf of bread and we sliced it somewhere in the middle and turned that slice to face you, it would have usually a square type cross section. So what we're going to do is we're going to slice my irregular shaped solid. We're going to turn the cross section to face you and see if we can write a formula, a function, a of x, for the area of that slice, and then we're going to multiply it by delta x, the thickness of that slice, to give its individual volume and sum them up. Let's go ahead and write that down. So we're going to take the area of a particular slice, multiply by the thickness of that slice, where this is the area of my cross section. Right, the slice turned to face you, multiplied by its thickness. This would be the volume of a single slice in my loaf of bread. And guess what? If we summed up the individual volumes of those slices from the first to the nth slice, for n slices of my loaf, and then let the number of slices go to infinity, we'd be left with dun, 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 the exact volume V will be given by the integral from a to b of a of x, some function that gives the area of a typical cross section, dx, where dx again results as from shrinking that delta x, right? Shrinking that delta x down towards 0, we're left with that differential dx. So this is what we're going to be using and applying today. The key will be our ability to write the area formula, a of x, for a typical slice. So that's what we're going to practice. All right, let's go ahead and take a look at then our 5-9 sheet, volume by slices. Sometimes the trickiest part can be drawing a picture, right? Can be drawing a picture. So we're going to bear with Mr. Fritz as he attempts to draw on the smartboard in front of you. Hopefully on your desk with pencil you'll do a little bit better with your drawings. Because visualizing this can be the most difficult part. So let's consider a solid whose base is a circle of radius 2, and whose vertical cross sections are squares. What? Well, I want everybody to think of paperweight here. Think of a paperweight whose base is a circle. Let's go ahead and draw that if we're looking straight down, right? Straight down the top view. The base of that would be a circle, so we can go ahead and draw that of radius 2. So first we'll draw the top view, and it has a circular base, right, of radius 2. And then if we were to take a cross section of that, that is my machete, and thwack, go ahead and do a typical slice. Right, a slice somewhere in there and turned it out to face you, what shape would it be? Well, it would be a square. What? If only we could visualize such a paperweight. If only someone took the time or had the inclination to find some such object, right? It would be a circular base, right? Circular base, but cross sections taken perpendicular to base that are squares. And if that is somewhat difficult to visualize, if only someone could take the time to find such a paperweight that was in fact sliced, whack, perpendicular to the base, and then turned out that cross section to face the class, what shape would it be? It would be a square. It would be a square, right, with a thickness delta x, right? And the area of that square, the base area of that square multiplied by that delta x thickness would give the volume of one slice. If we were to sum up these different slices given by the different colors here, we'd be left with the volume of the entire paper. Does everybody get the setup? No, we don't know how to do it yet, but we certainly have the strategy. So we're going to write an area function that gives me the area of this cross-sectional slice. Then we're going to integrate that area function across the range of possible slices, and that will yield the volume of this irregular shaped solid. Okay, so I'm going to leave these out here. Where else stay at? Okay. So let's go ahead and consider a 3D view. Now these are a lot worse, so I made sure that I showed the visual aid before I attempted to draw this. So here's our 1, 2, 1, 2, 1, 2. Here's our 3D view. Disclaimer, Mr. Fritz is not very good at drawing 3D views. That's why he's got the manipulative. Thwack. And so I'm turning on its side, and now we're drawing this. What? Yes, we're drawing this. It would be a square. And we take that out and we look at it and it's a square. So we've got a slice taken perpendicular to base. If we could pick up that slice and turn it towards you, it would be in the shape of a square. If you have difficulty drawing this, you're not alone. Right? I continue to struggle drawing these in three-dimensional views. Right? And so oftentimes I'll just do the two-dimensional view. I'll show where a typical slice would be, and then I'll draw an arrow there to turn out the face. Here's my cross section. All right, just like we did with related rates, right? Or oftentimes we wrote a formula, right? We wrote a formula that would deal with the quantities in question, and then we use substitution to rewrite that formula in terms of one variable or the variables in our problem. We're going to do the same thing here. So I'm going to write a formula for the area of that typical slice. Since it's a square, I could say the area of this slice is s squared, right, where my side length is s. And now I'll go back to my original figure and determine then if I can use, right, x's and y's to represent that, since I'm dealing with the coordinate plane with x and y. So let's go ahead and think back to the general form for the equation of a circle, right? So my base here of the solid is a circle. And what's the general form for the equation of a circle? Can we do that just to start our related rate stuff? X squared plus y squared equals r squared. Perfect. So for us, the general form for the base here would be x squared plus y squared equals 2 squared. Okay, does everybody see that? So my equation here for the circle, the circular base, is x squared plus y squared equals 4. Now the key will be to rewrite this area formula, which I have in terms of s, as a function a of x. Let's solve for y, right, that has x's in it. And so let's go ahead and consider this distance right here, where I've drawn my slice. This vertical distance here, right, would represent the y-coordinate of that point. Does everybody see this? Right here, that vertical distance right there would be the y-coordinate. it'll be given by y equals the square root of 4 minus x squared. However, this is only this portion of the base. Right? It's not only half of one side in that square. And so, if I wanted the entire base, right, I would need 2y. Then the area of that square would be given by twice that y coordinate, right? Once for above and once for below. Squared would give me the area of that cross section. All right, well, let's go ahead and solve this for y then. If I were to rearrange this, wouldn't I get y equals the positive and negative square root of 4 minus x squared? So we'll just take the positive one since we're going to double it like that. There we go. So we could take y equals 4 minus x squared. Now let's go ahead and write my area. My area of a typical slice as a function of x. And so we'll rewrite this 2y squared, but instead of putting y, we're going to put what? We're going to put square root of 4 minus x squared, absolutely. This is the trickiest part. If I can generate an area function, a of x, that gives me the area of a slice, no matter where I take it throughout the solid, then all I need to do is integrate that across the range of possible slices, just like across the range of possible rectangles for area. And let's make that look a little bit prettier. So this would be given by quantity squared, so the 2 squared is 4. The square root of 4 minus x squared squared is 4 minus x squared. So it looks like I'm getting 16 minus 4x squared for my a of x. How many mistakes did I make in that little squaring endeavor? You guys good? Now all we have to do is set up a definite integral that we get my volume b. And so we'll go ahead and set up a definite integral. In general, the volume, right, the volume of my solid with known cross section will be given by a definite integral from a to b of an area function, a of x, right, multiplied by the infinitely thin widths of those slices, d of x, and summed up gives me the integral symbol. All right, so for us, that would be the integral from leftmost x value of possible slices would be what? That would be the negative 2. So from negative 2 up until rightmost x value would be 2. My a of x is 16 minus 4x squared. And my delta x is shrunk to dx with respect to x. Now we're all set. Again, we could utilize the symmetry of the region. So what I encourage you to do, because this is a symmetrical spaceship, I would encourage you to consider integrating from 0 to 2 and doubling it, just because it will make your evaluations by hand so much simpler. And so instead of going from negative 2 to 2, let's integrate from 0 to 2 and double it. All right. Here we go. Let's find an antiderivative for 16 minus 4x squared. Well, we can do that. Easy cheesy. That'll be 16x and then minus 4/3 x cubed. Trying to fit everything here. Can I do it? I think I can. Did we get it all? 16x minus 4/3 x cubed. Great. From 0 to 2. Great. So it looks to me like it's going to be 2 times, and I'll go ahead and leave that out front, and we'll do my evaluation. 16 times 2 is 32 minus 2 cubed is 8 times 4/3 is 32/3. Are you guys getting that? Minus, here's the fruits of our labor. Lower limit all the way through is going to give me what? 0. Equals 2 times. And inside I've got 32 minus 32/3 would be 96/3 minus 32/3 is what? 64? 64/3? So my final answer would be 128/3. Or what, 42 2/3? 42 2/3?
42 2/3.
Awesome. Thank you. Wow. Who knew? 42 2/3 cubic units of space enclosed in that paperweight. Wow. Wow. What else can we do? Well, let's go ahead and try a different solid with known cross section. So consider a solid whose base is a circle of radius 2 and whose vertical cross sections are equilateral triangles. How are we going to visualize this? Well, turns out easier, I think. In fact, I think this is easier to visualize. And so let's go ahead and draw our base using a top view. Again, we have a circular base. If we missed that, we'll just move it. All right, perfect circle. Again, the formula for my circular base, general form is x squared plus y squared equals r squared. In this case, 2 squared is 4. And thwack, a cross section taken perpendicular to my base, when turned out to face the viewer, would be what shape? An equilateral triangle. What? Well, yet again, right? If we had the base of a paperweight that again is a circle, right? Is a circle, but now we've got cross sections taken perpendicular are triangles. We'd have like this mohawk top, right? This mohawk topper. You see it? If we were to take the slices of that and thwack, take a cross section, right, a slice, and turn it towards you, it would be in the shape of an equilateral triangle, right? If we summed up the individual volumes of those slices, we'd be left with the exact volume, right, of the solid. So you guys see the setup in this case? So we do that facing you. It's a pretty cool paperweight. In fact, I think I should consider leaving it out on my desk all year long and actually using it as a paperweight instead of just referring to it as a paperweight. All right, so let's go ahead and try the 3D view. I'm going to do our best again. So here's my 3-dimensional view. And whack. Slices taken perpendicular to the base come up out of the paper, right? Come up off of the paper as a equilateral triangle. You can choose whichever view. Oftentimes when I'm doing this, I just stick with the 2-dimensional view and draw that cross-sectional slice spacing. Our strategy remains the same. We need to write a formula for the area of a typical slice, and then rewrite that formula as a function of one variable, call it a of x, such that I can integrate it across the range of possible slices, which will yield the volume. Here we go. What, pray tell me, is the volume for the area of a triangle? Well, that's just 1/2 times base times height. It's just our goal will be to rewrite that so we have x's and y's, right, in it. So we need to think about the shape and how it fits into our picture. So here's our base is, well, that's the same base as our square. Wasn't our square, right? Had twice this y coordinate. So twice this y coordinate would give me the base here. So that would be 2y, right? That would be 2y. So my area would equal 1/2 times 2y. And then I need times the green height of that triangle. Oh gosh. Well, this is an equilateral triangle, so when I drop this altitude perpendicular to the base, it results in the creation of what little triangle? What special triangle? 30, 60, 90, where the ratios of my side lengths are, well, this would be 2y, so this would be 1y, so this would be root 3y. So it looks like root 3 times y is the green height in that triangle. 2y is the blue base in that triangle, as are any of the red sides. What? Oh yeah, the shortest leg length, call it x, doubled as the hypotenuse length, and the shortest leg length times the square root of 3 is my adjacent side length. All right, can we rewrite that in terms of x's? You bet your boots. Over here, I know that y equals, again, it's plus and minus square root of, right? Plus and minus square root of. I'll just go ahead and do the square root of 4 minus x squared. I can't do it though. If you want PDF, well, I can. I'll be thinking about it all night. I'll wake up, I won't be able to sleep. So I'm still going to do plus and minus, but we'll just grab the positive ones. Hang up I have. Let's go ahead and rewrite my formula now, a of x. Let's do it. So a of x will be given by, ready? 1/2 times 2 times y. What is y? Well, y is my root 4 minus x squared. So because that was a vertical distance, right? That distance above the x-axis is the y-coordinate of that point. When doubled, produces the length of the entire base of the triangle. So that would be 2y for the base of the triangle. Multiplied by 1/2 for my triangle formula, and multiplied by root 3 times y as the height for my special triangles, 30, 60, 90 triangle. And substituted back in produces an area formula that it gives x's in it, and let's make that look pretty. So let's go ahead and rewrite this again. How can we simplify this? Well, 1/2 times the 2 is just 1. Times root is just the 4 minus x squared and then the root 3 in front. So I'm getting root 3 times quantity, 4 minus x squared. How do we do? 1/2 times 2. Okay. Root 3 still hanging on for the party. Our y is root, and the radical times radical gets rid of it, right? So that came from that times that. Good. You guys okay? We do our setup? All right. So let's go ahead and find the volume by integrating our area function across the range of possible slices. My area function of a single slice when multiplied by the infinitely thin thickness dx of that slice would give me the volume of one slice. When summed up across the range of possible slices will give the volume of the solid. Let's do it. So again, leftmost slice, -2. Up until rightmost boundary of solid is +2. My a of x formula is root 3 times quantity, 4 minus x squared, no more radical. Dx. And now we're ready to go. I strongly encourage you to consider utilizing the symmetry of the region, right, and any constant multipliers out front so you don't trip over them to make your integration life as easy as possible by hand. And so I'm going to go ahead and grab onto that root 3 and put it out front. I'm going to go ahead and use the symmetry of the region to integrate from 0 to 2 and double it. Then my integrand function is simple and my subsequent evaluation is also simple. So let's go ahead and do 2 root 3 times an antiderivative function for 4 minus x squared would be 4x minus x cubed over 3. Evaluated from, and now I'm going to do the square brackets because I did a square bracket over there. And this is how my calculus teacher did the brackets. Our textbook does a straight line, so I was trying to do a straight line. And now this makes sense to do square brackets to bound that antiderivative function. Keep my constant multiplier out front for the end. And we'll do our eval. Top limit all the way through. So top limit all the way through. 4 times 2 is 8 minus 2 cubed is 8 thirds. Minus lower limit all the way through. Isn't that totally worth it? Just right there. That's totally worth it. A lower limit evaluation was so easy. Go ahead and simplify. I don't know the best way to do this. 8 minus 8 thirds would be 16 thirds. Ooh. And that in turn would equal 2 times 16 is 32 root 3 over 3. I know at least a couple of you would have guessed the exact answer of 32 root 3 over 3 before we started, but now we've in fact verified it. So the volume of this then would be 32 root 3 over 3 cubic units. Right? Interesting. Whew. How are you feeling, Philly? Let's do some more. Let's do some more. Let's consider a solid whose base is the region bounded by x equals y squared and y equals 4. So let's go ahead and consider different solids. So we're going to do the region bounded by x equals y squared and x equals 4. The key here will be getting a good picture so we can visualize it enough to write a formula for the area of a cross-section and then change that formula into a function of x, that I can integrate across the range of possible slices. So let's go ahead and draw my base first. This is, again, just 2 dimensions in the xy coordinate plane, top view. So if you're looking straight down, x equals y squared is a sideways parabola, right? It's a sideways parabola. So instead of opening up, down, it's going to open right or left. And so this one looks like positive x equals y squared, so this opens to the right. Let's go ahead and get some key points on that. So it would include points like 0, 0. Okay, that's good. We can do that. Looks like 0, 0. And how about 1, 1? And how about 1, negative 1? And how about 4, comma 2? And also then 4, comma negative 2? And x equals 4, oh, I can draw that. I got that one. X equals 4 is the vertical line. Here we go. So we're beginning to see a region take shape, the base of this solid. Just every time during 2A class. Okay, so there's the base of my solid. Now we're going to take a cross-section perpendicular to that base and turn it to face you. What shape will it be? Well, it's going to be a rectangle whose height above this xy plane that is coming out of the page towards you is half of the width contained in the xy plane. So let's go ahead and consider what that's going to look like. So I'm going to go ahead and draw a thwack, typical slice. And if I were to turn this slice out to face me, right, it would be what shape? It would be a rectangle. That's good news because we know the formula for the area rectangle. Whose height, right, so this height coming out of the page, then is half of its width that's connected in the xy plane. I'm going to go ahead and show this width down here is going to be blue. The entire, right, the entire base would be given by, again, double that y coordinate. So we're going to go ahead and do 2y again. You guys good if we do 2y again for that base of this rectangle? Okay, then the height of the rectangle will be what? It will be y, half of that. Awesome. Great. I'm going to try. Not making any promises, but I'm going to try. 1, 2, 4. So we took a cross section, perpendicular base, and turned it out towards you. It's a rectangle. This is coming out of the page. Right. The three-dimensional view is hard. It's hard for me to do. So it's okay if you struggle. The two-dimensional view is easier. The good news is that the two-dimensional view is what I'm going to use to generate my generalized formula anyhow. So let's go ahead and get some x's and y's and some area cross-sectional formulas here. Let's go. So what is this? Well, the area of a rectangle in general is base times height. The area of this rectangle in specific is base times height is 2y times y. That's 2y squared. However, are we going to integrate this with respect to y, or do my slices scan the solid from left to right? Well, my slices scan from left to right. So can I have y's in my integrating function? No. So I need to have x's in my integrating function. I'm going to have to rewrite this as a formula a of x. I'm going to rewrite this as a function a of x. So what's y given by? Y is given by plus and minus square root of x. We'll go back and we'll call this blue. Therefore, 2y squared will be given by 2, and what's y? Root x. So isn't my area function just 2x? That's it? Awesome. That's going to make for an easy integration. So that's root x, right? So that's 2 root x times root x is just 2x. All right, let's do it. So I'm wondering, how is it that we're crunch time? Oh, yes, because my carefully tailored lesson plan, right, didn't take account the Tuesday academic awards assembly schedule that was then used for the contact time assembly on Monday as well. So we got to go a little bit faster. Here we go. V equals integral of a of x with respect to x. For us, V equals integral of less than most x values of my region. 0 up until? 4. Good. A of x is simply 2x. With respect to x. Oh gosh, we can do this on one page. We don't have to go that down. Ready? X squared? Ready? Oh gosh. Minus 0. Yay! I like number 3.
Me too.
I thought, oh no, a parabolic base of the solid, and then the resolution. All right, guys, one to go, and then we'll do closure. Consider a lemon-shaped solid whose base is formed between y equals x squared and y equals 8 minus x squared. Whose vertical cross-sections are formed by slicing perpendicular to the xy plane, and they're circles. What? Well, we're going to try. We're going to try a setup here. We might have to cut out the last couple few to get to closure. So this is again a stretcher. We're going to do another day with volume. Okay, so don't think that we have to have it all ironed out today. But here we go. So 8 minus x squared. Oh gosh. All right, guys. So what are some key points? Well, let's go ahead and do y equals x squared. We've got that one. That's 0, 1, 1, 2, 4. And negative 1, 1, negative 2, 4. And then let's do y equals 8 minus x squared, whose y-intercept would be 0, comma 8. And who would open right side up or upside down? Upside down with the steepness of out 1, down 1. And out 2, down 4. Oh, that's convenient. So here's my intersection, right? Here's my intersection of the two parabolas, and it's lemon-shaped, right? This is like a lemon shape, and now I'm going to go ahead and I'm going to do what? Thwack. Yes, that's right, Marissa. I couldn't hold it back. I had to. Thwack. Slicing perpendicular to the xy plane are circles. And so here is my slice. And if I turn it out to face me, what shape is it going to be? A circle. And I know the area of a circle. The area of a circle is given by pi r squared, where my radius is shown here in blue. In my picture, however, where would my radius be? Would that be the length of the entire slice? No, that would be the diameter of a slice. My blue would be half of it, which makes this, right? Which makes this trickier. Or does it? What's the entire diameter then? Well, that would be, good thing we just did our area, right? That would be top curve minus bottom curve would be the diameter. So the radius would be half of top curve minus bottom curve. That is half of red minus blue. So let's go ahead and do that. Ready? A of x. It's going to be 1/2 of red minus blue. Red was a minus x squared. Minus blue curve was x squared. So I get 1/2 times quantity 8 minus 2x squared. So I get 4 minus x squared as my area function times 5. I just did radius. Yes. We need pi r squared. So squared is here. And we need a pi. It's going to go faster. So let's try this again. Ready? Pi r squared. So that equals pi r squared. So that equals pi r squared. Isn't the radius, sorry,
Oh, there we go.
isn't the radius that in blue?
Yeah.
Is half of
That makes
8 minus 2x squared? Okay, now we can square it.
Yeah.
Now we can distribute, now we can square it. And golly, folks, that's all we have time for. But you see the next, right? All you're going to do is integrate this area function in grade A of x across the range of possible slices. And we get those points by doing our little system. So what's this? 16 minus 8x squared plus x to the fourth. Okay. So we could continue on, right, just as we had in the past, by getting our points of intersection. However, with our shortened class schedule, we would want to get our closure. And so for area, we had a Riemann sum, and then a definite integral. For volume, we had a Riemann sum, and then a definite integral. And we could see these expressions again. We could see these expressions again. And so let's go ahead and write the Riemann sum that yields the area of an irregular shaped region, its corresponding definite integral, and the same for volume. So these are exactly what we wrote in the notes, right? These are exactly what we wrote in the notes. What I want to do in the last 30 seconds is, how would we find those points of intersection? Because we stopped it. So we still need the limits. How would we find these points of intersection? Set them equal to each other, just like we did to find the points of intersection when you're doing area. It's the same process, okay? And I don't want to leave that. I don't want to leave that out. Okay. Excellent work, you guys. I'll go ahead and save the recording. Nice job today.